So Paul, we've been surveying the sky, and I think there might be a problem with this theory of yours, which is we have gone and we've searched the sky now, and we have found the most distant quasars we can. And the most distant one that we found just a few years ago was at a redshift of 7.1. That means it occurred less than 800 million years after the Big Bang, or 13.1 billion years ago. And this object is incredibly bright. So bright, it would have to be more than a billion solar mass black hole. And I just don't see whether or not that's enough time to form something so big from nothing.
Well, you might think that forming a big black hole is pretty easy. Once you get a small black hole, maybe from the collapse of one of the first stars, we'll talk about them next time, and it will just suck stuff in. Splat. So you imagine black hole, eats stuff, eats more stuff, eats more stuff, gets bigger and bigger and bigger. No problem. Billion solar masses just has to eat a billion stars. Not a problem.
But these stars aren't going to be at motion, aren't going to be at rest with each other, right? So.
Yep. Well, let's think of the question. Let's imagine you're near a black hole and you want to escape. What do you think you might do? So let's say Brian was a black hole. I might think the way to escape would be to run away from him. But let's try that. So if there's an object trying to escape from a black hole, it's trying to run directly away. And it's slowing down because of the pull of gravity. It seems to have stopped. Is it going to get away? Is it going to get away? Oh, it seems to be turning around. So in fact, trying to run straight away from a black hole is not a very sensible approach. Here it goes. That poor star is doomed.
So, Paul, here in Australia, they always tell us that if you're out swimming in the ocean in the middle of summer, and there is a rip, that's where all the water runs out away from the shore, and you get caught in that rip, you don't swim against the rip, you swim sideways to it. That helps you get out of the rip and not die. So maybe that would be a good strategy here for the black hole.
Okay, well, let's try that. Here's the object moving at the same speed, but now at right angles to the black hole rather than straightly away from it. It looks like it's being sucked in.
Yeah.
It's getting sucked in. What's going to happen? What's going to happen?
Oh. So it orbits almost like a comet does, going around the sun in an ellipse.
And in fact, it could stay in this orbit for the age of the universe. Unless it loses energy or angular momentum somehow, it's just going to keep on orbiting quite happily. So if you're stuck in a rip or a black hole, go sideways. Don't try and run straight away from it. But that's the problem. Trying to form a massive black hole, that means we need to get matter down to a scale of about 10 to the 11 meters. But we need to get a billion solar masses in, and the stars typically spread over the size of a galaxy, which is more like 10 to the 21 meters.
So we need to shrink things by a factor of 10 to the 10? That's like shrinking you down to the nanoscale, to the size of a big atom or a small molecule. That's a lot of shrinking.
And all these stars out here are perfectly happy where they are. They're in nice circular orbits. They're not going to move in. A black hole isn't going to change that. Black hole doesn't suck anything more than the stars do with the same mass. If the sun was to turn into a black hole tomorrow, it will get very cold here, but the Earth would stay in exactly the same orbit. So how can you possibly get all this mass from such a large scale down to the centre so very soon after the Big Bang, when most galaxies haven't even formed?
That is a big mystery.